Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This will continue a conversation on continuity for differential calculus, and you should have already watched a video on continuity theory, types of discontinuities, and continuity on intervals. So you should have that down. Now we're going to get more into the wider range of how continuity can be used, specifically in compositions of functions. So let's start actually with not a composition, but a combination of functions. If you're given two functions that are continuous at a, and if c is a constant, then any arithmetic combination or scalar multiple of f and g is also continuous at a. That is my shorthand for the actual theorem. So let me actually show you what this means. That is for the sum and difference. It just basically means that if you know that the limit of your function f is f of a, that is, that f is continuous at a, and if you know that g is continuous at a, then their arithmetic combination, their summation or difference, is also continuous at a. So is the product and the quotient, as long as the quotient doesn't cause division by zero. The proof of this, well, you could actually use any of these. I'm going to, since I wrote those two down, I'm not going to prove either of those. Let's prove the quotient. So we'll start with what we're allowed to assume, that f and g are continuous at some point a. That's our if part. I'm not going to worry about the c as a constant business because I'm not going to bother with that multiplication. So my job is to prove that the quotient, the limit of their quotients, is also continuous at a. So let's go ahead and do that. Let's start with the fact that we know what continuity implies for the limits. So here are the implications. Limit as x approaches a of f of x is equal to f of a, and the limit as x approaches a of g of x is equal to g of a. There is one little condition when we start doing this division. We do not want that limit, g of a, to actually be zero. But we'll cross that bridge when we get to it. So let's take a look at the limit of the quotient here. Limit as x approaches a of f of x over g of x. We know by the limit laws this can be broken into two pieces. The limit as x approaches a of f of x divided by the limit as x approaches a of g of x. This is allowable because both of these limits separately, we already know, exist in our finite. There we go. The one thing that we can trade these out for are their limits, right? So the numerator becomes f of a, the denominator becomes g of a, and we will assume that g of a is non-zero, because obviously if g of a was zero, this quotient would not be defined. And this just showcases that the quotient f of x divided by g of x is continuous at a, because we could have just plugged in a to evaluate it. And that's how that proof goes. They all kind of go that way. They're very fast. Those are nice proofs. Very nice for most students and actually teachers to do. So let's dive into our first example. Assume, again for this example, that the natural log of x and the cotangent of x are both continuous at x equals pi over 4. That we are allowing ourselves to assume that. Use this assumption to evaluate the limit, and it should have had that in there. I just obviously didn't write it in my lecture notes. So anyhow, let's evaluate that limit as x approaches pi over 4. Well, because cotangent we're allowed to assume is continuous at pi over 4, that one's going to be the easy one. So let's go ahead and say this is equal to the limit as x approaches pi over 4 of the natural log of 3x squared plus 1/2 the cotangent of x. But again, we know that arithmetic combinations can be broken apart. And so because we know that cotangent's continuous at pi over 4, we're allowed to use that. We'll just say that that's equal to 1/2. I'll highlight this. This is equal to 1/2 cotangent of pi over 4. And we know that cotangent of pi over 4 is just 1, so that's going to be an easy one to get rid of. But the other one, the natural log of 3x squared, well, we don't know what that turns into offhand as x approaches pi over 4, but luckily we do know that the natural log of x is continuous at pi over 4. So I would love it if that wasn't the natural log of 3x squared. Luckily, we have algebra as our prerequisite, and we know how to manipulate these logarithms using properties of logarithms. The natural log, you can break apart a product within a natural log to a sum. This happens quite a bit in calculus, so you kind of have to get used to that. Remember, the cotangent of pi over 4 is 1, so I just replaced that. And this will be the limit as x approaches pi over 4 of natural log of 3 plus the limit as x approaches pi over 4 of the natural log of x squared. But you also know that you could take powers out of logarithms like that, so you could write the 2 out front. And now you do have the natural log of x. And we know, or we're told, that that function, natural log, is continuous at pi over 4. So we're allowed to trade out that natural log, the limit as x approaches pi over 4 of the natural log of x, just for the natural log of pi over 4. So let's see, this will be the natural log of 3 plus 2, natural log of pi over 4, and then plus 1/2. And this can be combined back up, honestly, if you wanted to. So this would be the natural log of, let's see, I can pull that back into the exponent, so it would be pi squared over 16. And the summation, you could write as 3 times that pi squared over 16. There we go. We were able to evaluate that limit using the information that we had continuity at pi over 4. That allowed us to directly substitute in pi over 4, only because they allowed us to. And that brings up a very critical point when you're dealing with limits. Up to this point, you cannot use direct substitution. You can't just plug in pi over 4, for example, in this case, unless you're told that it's okay. And we were already told it's okay if it's a polynomial or a rational function, but not for anything else. So that's why this problem started with, we are allowed to assume that both of those functions are continuous at pi over 4. But right after saying that, we get to the generalized direct substitution property. And the generalized direct substitution property basically allows us to plug in whatever our limit is approaching into our functions. The following types of functions are continuous on their domains. Polynomials, which we already know. So that means that if I have a polynomial and I want the limit as x approaches a, I could just plug in a. Rational functions, again, if I have a rational function and x is approaching a, I can plug in a as long as it does not cause division by 0. Root functions, again, same thing. If x is approaching a for a root function, I'm allowed to plug in a as long as that root function is defined for that. If it's a square root, for example, and plugging in a causes a negative in the radicand, that's a problem. But otherwise, as long as a is within the domain of that root function, it's good. Same thing with trig functions, inverse trig functions, exponential functions, and finally, the beautiful logarithmic functions. The implication of this theorem is tremendous. And when asked to evaluate a limit as x is approaching a of a function, this just basically means you could just plug a in as long as a is in the domain of the function. That makes this so much easier. Now, I really can't walk away from this and go to the next page because it's a theorem without doing an example. So I would like to do an example really quickly. So let's take an example like evaluate the limit as x is approaching, let's just say pi of, let's make something up here. Yeah, let's do like a secant of pi times x plus 2 divided by the natural log of x. And that wasn't supposed to be secant of pi, that was supposed to be secant of x. Sorry. So in this case, you want to check to make sure pi is acceptable in the domains of each of those functions. I definitely can plug pi into a linear function. I definitely can plug pi into the natural log because pi is greater than 0. And if you know your cosine, therefore you know your secant, you should know you can plug pi into the secant function. So because pi is in the domain of all three of those functions, lo and behold, this becomes the secant of pi times pi plus 2 all over natural log of pi. One thing I want to mention here is you should never leave a trig function like this if it's easily evaluated. And this is an easy evaluation. You should be able to do that. Secant of pi is a -1. So it's going to be a negative pi plus 2 over the natural log of pi. All right, there you go. We just finished that example, and I told you there was going to be a theorem on the next page. Here it is. Limits of compositions. If f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of their composition is going to be f at b. This is generally very challenging to prove, but let's just talk about this in easy terms here. So if we allow x to get really close to a, it should make sense that f of g of x, well, our argument on the inside must be getting very close to a, right? And we're told that as that argument on the inside gets close to a, g of x itself gets close to b. So I'm going to circle up in a different color here. That entire g of x, that should be getting close to b. And so intuitively, it should make sense that this is approaching, I'll write it that way, it's approaching f at b. That's probably a better way to go about that than trying to prove it, because the proof is a little bit gnarly. But that should be okay. When we get into actually using this, it's actually much easier to use than it is to say. In fact, let's go ahead and use it right now. You don't even know you're using it when you use this theorem. You want to look at the innermost function, just like you would actually in arithmetic, right? The order of operations. The order of operations would tell you, oh, look at what happens as x approaches e for the interior. Well, that would approach e to the pi power. So I'm going to write that in, actually, I'll write it down below. X approaches e, well, that implies x to the pi approaches e to the pi power. But x to the pi approaching e to the pi power implies the natural log of that approaches the natural log of e to the pi power. And we can actually do a little bit of good old algebra there. That's pi natural log of e, and we know the natural log of e is 1. So it's just pi. And now we know this implies that the sine of all that mess, x to the pi power, that's going to approach, well, sine of natural log of x to the pi, well, that's approaching pi, and sine of pi is 0. So in essence, when you're using that theorem, you're just basically saying, I'm working from the inside out. The entire time you want to make sure there's no domain issues, or that the range, the outputs of what you're working with don't cause issues for the next function in line. So for an example, as x was approaching e, I'll highlight that. If that caused problems with the argument of the natural log, let's suppose that caused the natural log's argument to be negative somehow, then we would stop, because there's just no way to evaluate that, because the argument of a natural log cannot be negative. So you have to be very cognizant of that. So every step of the way, I kept looking back to, or looking forward, I should say, to the next function in line. This x was approaching e. I knew that x to the pi was approaching e to the pi. There's no problem there. And then as you allow x to approach e, that means that the natural log of x to the pi, since x to the pi is approaching e to the pi, becomes natural log of e to the pi. Again, e to the pi is a positive number. There's no issue with that, with the natural log. And then I did some arithmetic, or I guess algebra in there. And then I grew to the most outer function and said, well, what about that sine of the natural log of x to the pi? Again, sine doesn't even have a domain issue, so I don't really have to worry about this, the value of this screwing up the sign. Instead, I just know that that value approaches pi. So perfect, sine of pi, and that becomes 0. That's the easiest way to do compositions in calculus. And on we go. We have a continuity of compositions theorem. If you have a couple continuous functions, one is continuous at a, that'd be g, and f is continuous at g of a, then the composition of the function is continuous at a. And we kind of just used that, actually. Again, this to me is a little more deep in theory than it needs to be for a Calc 1 course. Because most people are going to do what I did in this previous problem, which is I just worked from the interior and worked my way out. And each step of the way, you just make sure that whatever your output is not going to cause a problem for the function that it's the input for. So that's kind of an important statement. This theorem is usually proved within a textbook. It's not a terrible proof, but I think I'm just going to skip it for now, just because I can. All right, you've convinced me, I'll do it. Let G be continuous at A, right? That's the very first thing we must assume, because that's in the if part. Then that just means that limit as x approaches A of G of x is G of A. Now we're going to also assume that f is continuous at G of A. Well then, the limit as x approaches g of a, remember g of a is just a number, of f of x is equal to f of g of a, right? It's continuous at g of a, means you could just plug g of a in. A little bit of an interesting note here, g of a, we could replace that with, if that's the case, then the limit as x approaches g of a of f of x is f of g of a. Now, it might seem as though it'll be a little bit tough to get from here to where we want to be, but actually it's not too bad, because if we sub in, let b equal g of a, then we have the following. The limit as x approaches b of f of x is equal to f of b, right? But this allows us to use that theorem we wrote down a few minutes ago. Let me go back to it. It's this guy right here. As x is approaching a, g of x is approaching b. That's why I made that substitution. B is equal to g of a, actually. And so the limit as x approaches a of f of g of x is f at b. But remember, b is g of a. So the limit as x approaches a of f of g of x is f of g of a. And I've written it down here for your visual pleasure. It is not the easiest theorem to kind of wrap your mind around as far as the proof goes, but as far as usage, it's really nice. Except for the fact that I really never use it this way. Honestly, I do exactly what I've been saying the entire time, which is I just work from the inside out. And that's it. However, we can go ahead and do it again. So let's just take a look at this. Explain why, first of all, we have a function n of r equals the tan inverse of a -1 plus e to the negative r squared, right? Explain why that function is continuous at every number in its domain and state the domain. Okay, well, let's just deal with that first. Work from the inside out. Well, r squared, in fact, I'm going to call it negative r squared if you don't mind. Negative r squared is a polynomial, and as such, it's continuous for all real numbers. Notice I'm just working like the order of operations, right? Arithmetic before algebra, algebra before trig, trig before pre-cal, pre-cal before calculus. So now I'm going to hop outside of that exponent and into the larger function containing it. E to a power. Well, e to a power, and I wrote down e to the s here for a very specific reason, is an exponential function. And so it is continuous on all real numbers because there's no domain issues for e to a power. And I should mention here where s is equal to a negative r squared. I'm just going to put that off to the side. Now let's go ahead and zoom back out and look at the next function. This is going to be -1 plus something. I don't really care what the -1 plus something is, or I don't care what the plus something is, but it's -1 plus something. So I'm going to write that down. There we go. -1 plus something, I call that something t, is a polynomial, and so it's continuous on all real numbers. That something is just e to the s, where s is -r squared. You see what I'm doing? I'm just continually hopping outside functions. And now the outermost function, again following the order of operations, is a tan inverse. And again, tan inverse of something, let's see, I've done r, s, t, we'll do u. Tan inverse of something is continuous on all real numbers, because you should know that. The tan inverse is a function that looks like this. It even makes that sound when you draw it. And it has two horizontal asymptotes, one at -π/2 and one at +π/2. I'm going to tell you right now that is incredibly important to know as you move forward in calculus. So if you didn't know that's what the tan inverse looks like, get used to it. You got to know that. So working from the inside out, we didn't experience a single domain issue at all. And this is why that function is continuous at every number in its domain. And the domain is all real numbers. That's all I have to do there. Now, there are more rigorous ways of doing this, but honestly, to me, the calculus of compositions is a little too obscure for most people, and I just don't like to do it. Now, to use continuity to evaluate the limit as r approaches 0 for that function is super nice, because, I'll write this out here, n of r, because we know that all of those interior nested functions, those compositions, have domains of all real numbers, so they're continuous everywhere. So in other words, I could just plug 0 into n. So that's just going to be tan inverse of -1 plus e to the 0th power, which is tan inverse of 0, which you could see by my picture is 0. Very, very nice. You see how easy it is now compared to what we were doing previously when we were evaluating functions. Still with algebraic functions, you do have to do a little bit of algebra, but with these, it's just much faster. As long as you know that whatever your limit is in the domain of the function you're considering, you're good to go.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.